everybody here for the invitation and for the great discussions and the great conference that we've had so far. So I want to introduce something that has not really been central so far, but it has come up a few times, and that is to look at the kind of motivation to look at Fermi-Hubbard models beyond the standard SU2 spin 1/2 fermionic Hubbard model that we normally look at. For example, a couple of times we had already heard about SU3 models, or more generally SUN systems and other extensions to Fermi-Hubbard models that we can realize with other atoms than our beloved alkaline atoms, and in particular I'm going to talk about Ytterbium and alkaline-earth-like atoms. And yeah, so and what's the idea here? Yeah, I already mentioned we want to use these particular atoms, which are technically a bit harder to deal with, but we have good reasons for that, and the reasons for that are essentially the extension to the SU2 model that I mentioned, and the reason for that is a common thing that all these alkaline-earth-like atoms have. That is, they have a J equals 0 ground state of the electronic quantum state of the atom, and that decouples the nuclear spin so strongly from the electrons that any interaction term is basically SUN is spin state symmetric to 10 to the minus 6 or some very large suppression. So you do not see the spin state in the interaction term, and therefore the Hamiltonian becomes completely agnostic, symmetric to that spin state, in contrast to typically what happens in alkali atoms, where we have corrections that can be on the several percent level. In addition to that, we have two spin manifolds that we can use in parallel, and by this I mean the electronic spins with alkaline-earth. That's like in helium, where you have the spin singlet and the spin triplet manifold. Both of them have metastable or stable ground states. Both of them are J equals 0, so we have two separate degrees of freedom that are kind of orthogonal to one another, and so we have a total so how does this work? It's not moving. It's jumping. Okay, so in total we have 2 degrees of freedom. So in the vertical direction we would have this electronic manifold degree of freedom, and in addition we would have the nuclear spin giving us an extended spin symmetry for this Hamiltonian. Why is this interesting? As we would see, we can exploit this in various ways, and one important one is that we could make state-dependent potentials, and with this get some real orbital degrees of freedom that you would have in some condensed matter systems, but that are otherwise very hard to generate, in particular for fermions with a spin with cold atoms. And of course, in addition to that, there's all kinds of very interesting 2-electron atomic physics, molecular physics, Rydberg physics that you can do with these atoms that I'm not really going to talk about, but that can also be a motivation to use these types of atoms. Okay, so very quickly, where is all this coming from? Just this electronic structure that I mentioned. This is what that looks like. This is common to all the alkaline-earth. Most of you, I'm sure, have seen this before. And so just to remind you and give you the labels of the states that we are going to be talking about, we have the spin singlet manifold and the spin triplet manifold given by the electronic spins, the coupled electronic spins, and within the two we are going to work mostly with the two ground states. The excited state of the triplet, that's the one that is really the ground state of the triplet manifold, we call that the excited state, and the ground state, that's what we call the ground state G, is the ground state of the singlet manifold, and that's also the overall ground state. And between these two states there's the famous optical clock transition that these modern optical lattice clocks use to measure time. And that's because this transition is extremely narrow. Decay rates are, depending on the isotope and the external circumstances, are on the many tens of seconds range. So for our purposes, this is essentially stable. Okay, and so what can this give us? And to give one particularly extreme example that has everything in one, is that we can now, in the Fermi-Hubbard context, we can now introduce all these degrees of freedom, and we can say that, for example, we use these internal states, the electronic internal state, to define our orbital states, like I said, and this internal state becomes an orbital state in such a way that I design the system to be, for example, localized for one state of this spin 1/2 degree of freedom, of this 2-state degree of freedom, and then design it in such a way that the other state would be mobile in my potential that I'm generating with my optical lattices. In addition, as I said, we still have the nuclear degree of freedom that is free, so this gives me a spin degree for the underlying Hamiltonian then. And on top of that, of course, I need interaction terms. Now I have two different manifolds that behave very differently. They also have very different interaction properties. So now I have interorbital, intra-orbital interactions, and they can also be spin dependent in that case in such a way that we can have active spin exchanges in the collisional process. And then this could look like this, like it's sketched here, where we have a it's not working so well. So use this. Where we have an atom that is essentially seeing a very deep potential in one state, and it can collide with a moving other atom that is in this blue state, is not localized, is moving around, and in this collision it can transfer momentum. Momentum can be transferred to the moving atom, but also the spin can be transferred. You have probably seen this, particularly in the context of Kondo systems, and this would be the Hubbard-style Kondo Hamiltonian, where we have spin exchange together with these localized and moving atoms. So this is definitely a motivation to be able to have all of these conditions, all of these ingredients together in one Fermi-Hubbard Hamiltonian. Very quickly, where does this orbital property come from? Most of you will know this. The fact that electronically the two orbital states, this E and G state, are so different means that they interact very differently with light. And so if you could look at the polarizability curves as a function of wavelength, then the blue and the red curve, they look very different. And so now by choosing the wavelengths of, for example, my lattice light, I can now choose how deep the lattice is that the atoms see. The classical case that to operate with, and this is what we do most of the time, is we choose this point where the polarizability is the same, so both states have the same mobility. This is the so-called magic lattice that is important also for the clocks. But you can also do the opposite. You can do the anti-magic lattice, which is very interesting, where the atoms of the different states are localized in different sublattices. Or, and this is the scenario that we are using in this example, in the next example, that is where we have a localized / mobile combination where we localize one of the states, the excited states in particular, and the G atoms, the ground state atoms, can still move around in this lattice. Okay, on top of that, it turned out, and it came a bit unexpected, that we can actually also tune the interaction strength, and here I'm talking about the direct interaction strength between two fixed spin states, one in the E state and one in the G state. So these so-called orbital Feshbach resonances that we discovered only exist between those particular combinations of states, but like for example when two orbitals, the inter-orbital interaction is then tuned by this resonance. That turns out by some coincidence to exist both in 171, in the fermionic isotopes 171, 173, and for 171, in the example that I'm showing, it looks like this. What we found is that there's when you do the spectroscopy of atom pairs in the lattice, this is our most precise method how we can do this. So we prepare spin up-down singlet pair on the lattice side, then we do spectroscopy, bringing this to a still, for example, spin up-down combination in this example. But now with the ground state and the excited state populated in the same lattice side. So when we do this, we find an interaction shift of this transition relative to the bare transition. This tells us essentially the energy of this new state that we have created, and this is the state that is affected by this Feshbach resonance, and then by changing the magnetic field, what we find is that the energy, the repulsion basically changes here along the magnetic field axis. And by analyzing the spectra like this, we can reconstruct the Feshbach resonance, and what we then find that for Ytterbium 171 in particular, there's a Feshbach resonance is 1,300 Gauss. That is fairly broad here with a delta of 400 Gauss that we can use to tune the interaction strength in these systems. I should point out, though, that's a bit interesting from the molecular physics point of view, that this is only broad because the magnetic moments of these atoms are extremely small. From a Feshbach physics point of view, the energy shifts that we are talking about here are actually quite small. So from a Feshbach physics point of view, this is actually a narrow resonance, even though it looks very wide on the magnetic field axis. Okay, so now what can we do with this? We can implement what I introduced before. We can implement now, use our state-dependent lattices, introduce a lattice that localizes one state of the system more than another, and then populate this lattice with atoms of these various states, with, for example, a mixture that we can prepare with various ratios of occupation and various densities. And one thing that we recently looked at was to look at transport in this particular scenario, and this is then also described as a heavy light system, where we effectively have now two populations moving in the same lattice, and we can also describe this as two populations of atoms where one of them has a much larger mass than the other. So this would then be equivalent from the, for example, group velocity point of view, but the way we realize is that effectively the lattice is deeper for one species than for the other. And so, yes, please.
And densities are equal?
This we can choose. In the examples that I'm showing, the densities are, let's say, similar, but we would, for example, typically have more, in this case, of the light atoms, which are blue and delocalized, shown here. But that's negotiable, basically.
And it's a 1D lattice?
Yes, exactly. So,
you can find in the other two dimensions and just... So
yeah,
1D in a sense, not pancakes, but really just 1D.
Right, that's correct. So this is a system of many 1D tubes. That's how it is prepared. We could also do this in 2D, but the examples that I'm going to show are in 1D in particular. Right, and so what was interesting here is that we were to look at this heavy light mixture. Is a famous example of where it is expected that transport and relaxation would be inhibited in a kind of similar way where to what you would have with disorder in a system. Well, not exactly similar, but let's say similar looking from the outset, but with the big difference that there's no disorder whatsoever in the system. Theoretically, in the theory, the system is completely translationally invariant, and so this has been a famous thought experiment to do these mixtures and think about and try to calculate what happens to the relaxation in that case. So the way we probe that is that we prepare the system initially in one location along the tube, and this would be then a density profile after this preparation, for example. We then move the confinement along the axis of the tube, and in such a way that the new equilibrium position here is, for example, moved quite far. Let's say it's over here, and then we see how many particles have been transported from the left to the right, for example, or or how the system, in more generally speaking, how the system will respond as a function of parameters. And in particular, the important parameters here are what is the difference in mass, so what's the difference in tunneling speed between the two components, and what is the difference in and what is the interaction strength between the two. So in this case, I should point out there's essentially two fermionic components, but each of these are spin polarized. So there's no additional nuclear spin in the system. We can populate them, or well, we don't have to. We can do actually mixtures with different spins, but we don't necessarily need the spin here. The interaction that we are interested in here is the one between the two orbitals. All right, so the purely intra-orbital interaction, the one that we can tune with the Feshbach resonance. And there has been a lot of theoretical work about this. Generally speaking, there was for a long time there was also a dispute whether transport on long time scales would be completely suppressed or just completely stopped, or just suppressed to very slow diffusion type motion on long time scales. There was an influential paper, for example, which just inspired this plot by Norman Yao and colleagues that did this calculation. Well, this is our calculation, but it's basically copying their parameters. This was exact diagonalization, small system of length 8, where they're looking here at the time evolution of some kind of excitation that is relaxed via transport, and then you see this behavior that, okay, on one thing it has a very funny shape, but what's more important is if you look at the time scales, and this is the time scales in unit of the tunneling speed of the light atoms, you can see that these time scales are dramatically large, and the blue and the red curves here look at the relaxation of the heavy and the light particles respectively. Now, one big thing at the time was the fact that you seem to find these plateaus that arrest the thermalization here for long periods of time until there's again an onset of motion. That turns to be out to be probably largely affected by system sizes. You can do other calculations where this effect is much weaker. You always have these kinds of artifacts. But what's definitely common in all of these cases is that you have a relaxation scale that is many orders of magnitudes larger than the individual motion time of either, the motional speed of either of these two components. When we do these experiments, then if we want to look at this, then we actually don't do it quite as dramatically as I showed in the initial example, but rather we do it in such a way that we only displace the system by a little bit. This is to avoid having overly much Wannier-Stark localization, things like that. All kinds of different effects have to be considered, and it gives us better access to this long-term relaxation. So what we do then...
Is this just the ground state density, or is this...
What's measured here is the ground state density, so the light particles, the faster moving ones. We can also detect the heavier ones, but it's much worse, the signal is much worse. So we can't really see all effects there in the same way.
And the potential is displaced equally for the heavy and the light particles?
Yes, that's correct. Mm-hmm. So there's... the potential is moved in such a way that both particles see the same force initially and then move in the same underlying potential. And what you see here is basically that the position has been moved from over here to the dashed line. That's a relatively small step. And then what we do is we look at the initial state, that would be the gray, the lighter curve in all of these diagrams. And then we wait for some time and see, check how much the distribution has changed. So how many particles have now moved, continued to move to the right in this case, basically. Okay,
So
and then yes.
I'm still trying to understand your results. So basically, if you think of the heavy particles as frozen, just I know they are moving, but on some slower time scale. But say I freeze them, then that forms some kind of a random potential for the light ones.
Right.
So basically, the light ones should get localized because in 1D, any random potential
Yes.
should localize them.
Yes.
Am I seeing that here in these plots? I couldn't quite make out.
Yes and no. So the main effect that we're interested in is from the part of the system where the heavy particles are not localized. And so they are both moving on relevant timescales. That's definitely an important, because otherwise, like you say, you would directly get a localization due to the random potential that's created by the heavy atoms. Some of the heavy atoms do get localized because of Wannier-Stark localization. That's at the edges of the system. We had to take that into account for the analysis. That's why it became quite complex to analyze this data. And there also then you co-localize the light atoms. You have to basically take that out. But in the scenario that we are looking here, it's then the contribution of where both components are moving.
Okay, but is there like as you read across, is the time, what is changing?
Yeah, so that's what's going to be the next thing. So what's always in light color here is the initial state, and then what is plotted in the darker color, that's then the evolution after some time. And you see that always there's some kind of displacement here for this system. The upper one is here, the stronger one. And so what we then quantify is how much the system changes as a function of time, essentially. So since we cannot really fit this with a analytic function. And then if we plot this relaxation process then as a function of time, then we get these types of curves. And so we have to unpack this here. This is now comparing two different scenarios. That is the scenarios where there is either a significant but not super dramatic, a factor of 5 difference between the tunneling speed of the light and the heavy particles, whereas there's a much stronger factor of 10 ratio between the two masses or the two tunneling speeds in the other case. And here what we then find is that as we now look at different scenarios with respect to interaction, so the gray curve being the non-interacting case, and then there's a interaction with then there's different interaction strengths here. So we either have U over T of 2 or 10 essentially for the light and the dark blue cases. You can see very different behavior. And for the non-interacting case, what we find is essentially that the atoms that are not stuck in Wannier-Stark physics, they move initially together with the potential, and then there's no further relaxation as expected. So this is kind of the baseline, how we get a flat potential here. But then what we find is that for low ratios of mobility between the two cases, there's not a very strong interaction effect of adding additional interaction. between a strong and not so strong interaction, and you get a relatively benign behavior here, and this is expected from the theory, whereas we can see a much more dramatic effect, and this is basically what's then giving us these expected very long timescales of the relaxation when we do this at a larger ratio of, in this case, 10 in the tunneling speed between the two components and u over t of 10. So what you can see here is that the more strongly interacting system is much more dramatically slowed down compared to the, both are slowed down, but it's, the effect is much stronger in the case with larger interactions. And that is expected in the sense that this exponential increase in the relaxation time comes from this particular interaction between the two orbitals here, the two components in the heavy and light case. So there was apparently a long-standing discussion that I learned in that context whether the motion would be expected to be entirely frozen. I think the consensus now on the theory side is that this is probably not the case, but you would expect diffusive motion with very long time scales in that end of the spectrum. Okay, so this is using this one degree of freedom, essentially, the orbital degree of freedom that I introduced in the beginning, and then there's the other kind of the opposite degree of freedom that we've been looking at again more recently, which is to take the completely regular Fermi-Hubbard model as we all know it, but extend it to the SUN system. Then of course the Hubbard Hamiltonian does not actually change at all. The only thing that changes is that we're summing over a bigger index. Then now you can immediately see that this is going to change the physics. If you think about the magnetic correlations, obviously with SU2 system we all know we get some kind of antiferromagnetic type correlation between sites, but if I'm now thinking about a system that has 3 spin states, this can automatically not really look exactly the same way, so something else would have to happen, and this is not what is expected to happen in the ground state, but you can see that you need other magnetic correlations, and there has been quite a bit of work, and that's a little bit older, where people have looked at these lower SU3, SU4 systems. In SU4, for example, you would expect for very low temperatures something like a valence bond state system or even plaquette type systems. And then for larger N, kind of all bets are a little bit off, then people often start to approximate this with the large N limit immediately, anything above 4, depending on who you ask, I guess. Interestingly, the system is significantly, this is more than just changing the number n, because the situations that you get differ not just in the geometry, but also in other, you can have other important qualitative differences. I think Gaten will talk more about this in his talks. This also, for example, one thing that you can see immediately is that if you say you choose SU3, then half filling in that system is not the same as integer filling as it would be in SU2. So that gives you a very different relation between these 2 points and Fermi surface relations in such systems. So it's, of course, suddenly quite a different scenario. And then I already mentioned this exotic magnetic ordering. Also then what people expect with newer work, for example, in the SU3 system, something that, well, now I guess it also pops up in the SU2 Fermi-Hubbard system, but with the doped systems, but that here, in some people predict at least that there should be the order, different orders as a function of temperature. So as you go down in temperature with the system, you don't have something like the antiferromagnetic order that shows up at relatively high temperatures very weakly and then increases the correlation length, but rather you go to a fundamentally different geometry as you get colder and with the system. And I don't know how many there can be for SU3. I've seen 2 different phases for different temperatures, but of course it could be arbitrarily complex for higher spins. Okay, how do we do this? Well, we can actually vary the number n in our Hamiltonian. That's fairly trivial. We always start with the physical system of SU6 because Ytterbium has a spin 5½ the interesting isotope 173. So we start with an SU6 system. We remove as many spins as we choose, and then we can set an effective system, like for example an effective SU4 system here, which is SU4. It's not really a spin 3½ system, because if you change the magnetic field it does not rotate in the same way, but for the Hubbard Hamiltonian it's a full SU4 symmetry. And our what we have now recently done is that we have changed the system, that we've upgraded the system to do full 2D loading. So what we do for these experiments is we simply prepare a single plane of atoms and add then an orthogonal in-plane lattice. So the scenario is something like this. We have an orthogonal, regular, normal Fermi-Hubbard model with the square lattice, and then we image through that plane orthogonal to that plane. And this allows us to have a relatively high resolution, but not single-site in situ imaging, so we can measure local quantities and measure things like, because it's 2D and there's no averaging, we can measure more complex things like fluctuations, for example, of atoms, to measure things like compressibility, as we'll see in a second. As you all probably know, of course, unless we do special potentials that are homogenized, we always have a parabolic or otherwise confining potential. That's the case here as well. So we always get a measurement that measures many points with different chemical potentials at the same time. And then it looks like this. We get the scenario where when we load systems, and this is not quite individual shots, but very few shots average, we get images like this. For weak interactions, we increase the interaction strength, and then we get this core that slowly shows up. And already here you can see that as you do that, we get this classic Fermi-Hubbard type behavior where we get a drop in compressibility for integer fillings now in an SUN system. And that's, of course, then very nice. Of course, the first thing you do is you go to high fillings to see that indeed you can have a fermionic Mott insulator with more than 2 shells.
Were the bottom shots radially or azimuthally average?
No, that's why the noise is so large. This is literally just 1 row of pixels, or 2 rows of neighboring pixels. Yeah. So the next, the other data sets will be. We can also look at the distribution of occupation numbers. That is something very simple that's been around for a while. It's interesting here because we can basically do it in situ. We can do photo association, what you all saw with the microscopes, what happens during the microscope illumination, we can actively drive that by doing photo association of pairs, remove all the pairs of the system, and then basically see where are singly occupied sites and where are sites with higher occupation in our system. And then we can indeed identify that as we do this. So this is the same data set. If you remove all the doubly occupied sites, and we can see that slowly in the center there will be this region of double occupation. That can be removed. Okay. Right. So now we can do the azimuthal averaging that Caden would like to see, because that, of course, the data becomes nicer. But in particular, also we can then use our knowledge about the trap and convert everything to a chemical potential description. So now we can plot these curves as the function of the chemical potential and start to compare with theoretical predictions. And up until not so fairly recently, there wasn't really that much around. Last time we looked into something similar, we basically had something like high temperature series expansions for very deep lattices, and then non-interacting system for very weak lattices, and that was pretty much what we had. In particular, the interesting region in between, we didn't really have anything that would help us, and we didn't really look into that then very much. Now we have from Caden and his colleagues that are also here, we have nice theory that we can use to compare what actually happens in this intermediate interaction strength system, and we can quantitatively compare the two. And that works quite nicely. So this is NLCE and DQMC model. So most of this, I think, in this plot is this linked cluster expansion data that we are fitting essentially to the data. We heard in this conference that we are not supposed to actually be so cold, apparently, anymore. And so we like to hear that as the experimentalists. So one thing we can certainly do is vary the temperature going up. In the previous data set, I should say, we try to be at a temperature that allowed a large range of theory to be applied, because I cannot go to arbitrarily low temperatures. Here we actively go to higher temperatures by essentially introducing a heating rate and seeing what happens. And we can, of course, then see how the heating changes also the intrap temperature that we measure. No surprises there, but you can see that also the theory matches this, and in fact we get better matching between what we measure and the theory for higher temperatures so far. in typical cases. We can also, of course, compare the different values of n. In this case, of course, so far I've shown you the n equals 6 in the native case that we are typically looking at. You cannot see gigantic differences here. If you look at these quantitatively, in particular if you compare it with SU2, you can see tiny differences in the density distributions due to this modified quantum statistics. But of course, the curves, generally speaking, as long as you don't go to very large n, where you would have full Pauli blocking, they look fairly similar. But we can verify this here also quantitatively. And interestingly, what we can then do is we can start with a fixed system, for example, at a fixed temperature for different n's.
Why don't you have theory on the U equal 2.3?
Yeah, I wonder why. Yeah, so that's where the theory did not yet go to the temperatures, down to the temperatures for this particular data point. But I heard that's almost basically possible.
Yeah, so
What we can do.
yeah, so essentially, like, we have been doing the QMC and NLCA, and for the NLCA it works best at large U, because you can also truncate the Hilbert space and such. The DQMC works better at lower values of U. However,
Also, the T over T tends to increase with larger U. That also makes it easier for the theory.
So the data at U equal 2, it's colder than the one at larger values of U, so that also makes
In
the
units
calculation.
of tunneling, I should say.
Yes, in units of the
Absolutely,
tunneling.
it's a bit okay.
So yeah, if I remember correctly, the one around U equal 10, maybe it's around the tunneling, but the ones at U equal 2 is around like 0.3, maybe. And the thing is, like, even, well, in this case, we also have a sign problem, and the sign problem gets worse with n. And I think Kaden will tell you more about this. What is it, the propagation of misery for all these different numerical techniques that we have?
Right.
So,
All our
yes, now
numerical
we're
techniques fail here.
working on that.
Okay.
So just to
Yeah, so,
understand,
yeah.
this is repulsive field, right?
This is repulsive, yes. And this is fixed because this is the intra-orbital interaction. This cannot be tuned with the Feshbach resonance. Okay. Yeah, so but what we can do is, because we can fit in this entire range, is what we can do is to look at things like temperature evolution. So this is a bit preliminary as we go into the lattice, which is always interesting for us to see how adiabatic we can load the lattice. And here, what we find is actually something that we've suspected also before, but couldn't see it so well. There's what we can see here is a general temperature evolution that's kind of as expected. So if you plot the temperature in units of the interaction strength, as soon as you go beyond a certain U over T, and this we are here already where the theory starts at 7, then more or less the temperature would scale somewhat with the interaction strength as you ramp up the lattice. However, if we now do this and compute an entropy from these values, and what you find is that we start with the same temperature and entropy in the non-interacting system, and then what you find is that systematically the higher the n value is, the lower the temperature in these U units. That's the Pomeranchuk effect, where you get somewhat lower values for the spatial degree of freedom here. However, when we use the entropy, then instead, and we extract from the theory the entropy and plot that as a function of this ramp, then we can compare this to the initial entropy that we have before the lattice is applied. This is the flat line. And we can do a round trip measurement where the system goes into the lattice, we bring it back and measure the entropy after that, which is obviously higher because we heated the system as we are never perfectly adiabatic. And then there is still a bit of a question mark here as we see that typically this fitted entropy that we get out of the model tends to be higher, as high or higher than the round trip entropy that we measure. So this might be a not perfect adiabaticity for the deeper values. It's not entirely sure. As we see in the next slide, we can cross-check that to some degree. But yeah, we see that generally it's the same behavior at least, but yeah, we have this weird different order than it should be. Going back to this, we can actually, as I said, measure also more complex observables like fluctuations, and this gives us a separate access to the temperature, and this is kind of neat because what we can do is we can look at the density distributions like this, combine many of them, look at the averages, but also bin pixels and look at fluctuations within certain areas. And this then, of course, gives us fluctuations that in the thermodynamic limit are going to be, for example, given by the fluctuation dissipation theorem. So if we now bin the variance and combine this with the compressibility that we can also extract ideally without a model directly from the data, because we know the dependence of mu in the trap, and we can measure the density, so we can just derive the data to get the compressibility. Then we get a kind of model-free temperature that we can use then, or here it's plotted the other way around. We are plugging in a temperature that we know either from a fitted model or that we just fit, and then we can compute here the expected fluctuations for this particular scenario here from fluctuation dissipation theorem in this black curve, and then you can see that you can actually resolve that enough that you can locally resolve the temperature in these systems. And finally, then you can do you can match these two and do this with the full data. This is a bit messy. We are calibrating this a bit better, but you can already see with a better data set. But you can already see how this roughly works. And this, if we now plot this again the fluctuation as a function of the local density. So basically, we are comparing, we are combining points that have identical density. Plot the fluctuations again, compare it with a fluctuation dissipation prediction that's coming from the local compressibility as well. Then you can see how this evolves as we go into the lattice, and you can see that if you now compare the best fit with the fluctuation dissipation theorem and the temperatures that we get from a cadence model, they are similar, not quite the same, but they kind of track nicely, and already in this data set you roughly see the features that you would expect for this particular configuration of the system. And then here we are comparing these two. The error bar should get still a bit better. You can see how they do evolve kind of similarly. So in that sense, we can agree, we can say that these two measurements at least agree, at least within the error bars so far. So that seems to work well. Right, okay, so yeah. Hayden is not yet nervous, but we already gave half his talk.
It's lunchtime. Anyone can walk out when they want.
And right, so yeah, to summarize, I wanted to advertise alkaline-earth atoms, and in particular for us the Ytterbium as a system to have more extended Fermi-Hubbard models that where we can get these additional properties, orbitals, extended SUN symmetries. And of course, yeah, we are not the only people doing this. There's also great work in groups like in Japan, in Kyoto, and Boulder. And of course, now increasingly there's theoretical work available for this, in particular for the SUN case. We can implement now state-dependent mobility in practical ways that we can really introduce two orbital properties to models. And yeah, this then allows us to hopefully look at many interesting questions. One thing, of course, would be nice to go to really lower temperatures and look at these magnetic orders structurally, and look at maybe these finite T scalings. Dynamics would be interesting, and of course the quantum-type systems with the spin exchange is something that would be very nice to implement. And finally, I should thank the people who did all the hard work on this. Mostly this was done by Giulio, what I showed you, Giulio, Oscar, Nelson, and with the setup also being done by Luis and Alex. And of course, the theory group and from Rice did the theory for the SUN systems that I showed, and for the transport we collaborated strongly with Michael Knapp and Philipp Zechmann from TU in Munich as well. Thank you very much.
I'll take the chair's prerogative to just say also Richard Scalatar was on the theory team there.
Oh yes. Yeah.
So questions?
What's the prospect of getting spin-resolved imaging?
That can be done, yes. Mm-hmm.
So you just don't do it right now?
We do it, but in this data that you saw, this has not been resolved. Yeah.
And on the last part where you did the fluctuation dissipation relation checks, do you get also non-local fluctuations, or is it only based on the local fluctuations? And is that checked that the non-local fluctuations don't play a role in case you don't see them?
By non-local, you mean like particle hole?
Yes, the density is correlated over some distance. If I remember correctly, in this relation, you have to sum over all local and non-local fluctuations. And we did this with lithium in the microscope, and it was about a 20%, 25% correction. But I think that's temperature dependent and density dependent. So
Yes, normally that should be in here. Yeah, so yeah, then there's also the difference. I didn't put that here, where when you have the really local, so the on-site additional like coherent admixtures and so on, those fluctuations. But those are removed because we also don't see them since we don't resolve them. So you have to basically get the length scales right to get the fluctuation dissipation theorem.
Does it exist out automatically? Because I remember there was a paper from Michael Köhl where they were explicitly seeing basically this gap between.
Yes, yeah, that's exactly that. That's what they compared there in that paper. Yes.
Are those the plots you showed me yesterday?
Yes.
It's a pretty big gap. It's not a 20% gap in your case, is it?
That depends on where you are in the diagram. Yes, it's very strongly different for different, especially different diffraction strengths.
Any questions?
Yeah, I have a question up here, sorry. So for preparation, let's say one way to go, of course, is to just cool everything down and you guys fight hard and everything, right? But let's say if I want the square lattice for SU3 with these sort of stripe type of patterns, could you like use some spiral to imprint exactly this SU3 state and try to, actually already put the order in by hand, but then, start from that state, let it go, see how long it lives?
Depends on what exactly you want, but many things should be possible, yes. Especially the. I'm sure you will find something that's super hard, but
right. But
yeah.
Is that something you would consider? I mean, sometimes I feel like it's actually kind of broadly, like the experimentalists always want to fight hard to show that their order emerges without biasing the system into the state, and I get the idea, but as a theorist, I would also say it's interesting too.
Yes, no, absolutely. That's.
Maybe just following up on this. So here temperature is much more of an issue because, like, okay, more or less you are dealing with very fragile states. So ordering temperatures should be much smaller than the CO2 ordering temperatures. So, like, well, this brings the question. Actually, are you optimistic about sort of reaching necessarily low temperatures to see those fragile orders?
Yeah, so that kind of depends very strongly on A, who you ask, and B, which state you are talking about. So clearly, when we're talking about some big SUN generalized singlet that's spanning many sites, I would expect the system to be correspondingly, there should be higher order terms at some point coming in, or at the very least, like you say, very fragile against any non-homogenities and all these things.
But just requiring low temperatures.
Pardon?
But just requiring lower temperatures to be observed.
Yeah, so the onset of magnetic order you would expect, I think, to be on the same scale. So that's the shorter range order, yes.
Okay, well, short range, yeah.
And then, yes, and then.
But that's not good enough, right? You want to see exotic order.
If you want to, yes, exactly. So there have been theory proposals that say essentially for the higher end cases that the scaling is not. They have been looking at particular states though. That it's not like you have to go to t to the 4 u over 5 t cubed divided by u squared for SU3 for all cases, and end up at similar temperature ranges. Whether this is even for maybe not infinite long range order, but the way you would see the non-trivial order that should show up. But I mean, these are all these earlier papers that try to look at close to t equals 0 with various methods. I don't understand the limitations of the methodology well enough to be really sure what this means. Yeah.
I feel like I'm missing something, but if you have spin resolution, why don't you just check for your shorter spin correlations?
We have spin resolution, but not on the single site level.
Oh, that's the point, okay.
But they could do it with the fluctuations, by measuring the fluctuations for some of the spins, and that should give you some indication.
Okay, but why don't you?
In some scenarios, yes. Yeah, that you don't see all types of fluctuations, and then you need to have a pretty good idea of what you should see and so on.
Yeah, maybe we should head to lunch.
Here, there's another question.
Just out of curiosity, quick question. Why is n equals 5 not included?
Well, the real estate on the slide is finite. No, we can do all of this with n equals 5 in the same way. It's just that things change kind of logarithmically with n. So the largest changes come in the beginning, and then you go 2, 3, 4, 6. There's not a huge difference between 5 and 6, unless you go down to the complex long-range ordered states that you expect very close to t equals 0.
All right, I think that's a good place to stop. Let's thank